Welcome back, everybody. We continue with part 3 of the mini course on nonlinear Grassmannians and finite manifolds. Today's lecture will be given by Stefan Haller from the University of Vienna. Stage is yours.
Thank you for the introduction. Let me begin by thanking Pauli and Francesco for the invitation to give a mini course here together with Cornelia this month. In Cornelia's talk, we learned about dual symplectic pairs, decorated Grassmannians that pop out of these dual symplectic pairs, and symplectic reduction of these dual symplectic pairs that can be used to describe coadjuvant of certain groups. In particular, she talked about the ideal fluid dual pair. And I would like to continue here in the next two lectures. Today I would like to talk about contact manifolds. In particular, I would like to talk about a dual symplectic pair that is naturally associated with contact manifolds, or with a contact manifold. And I would like to show you how this leads to certain decorated nonlinear Grassmannians, how they can be used to describe very specific coadjuvant orbits of the contact group, and how this dual symplectic pair can be used to describe singular solutions of the Euler-Maclaurin equations on the contact group. So this is the rough plan. I will start, since it's a mini course, I'll try to go slow. We'll start talking about contact manifolds a little bit. Then I will discuss a very natural construction, so-called symplectification of contact manifolds. Every contact manifold can be turned into a symplectic manifold in a canonical way. And actually, we will look at this construction and generalize it in a very natural way to produce an infinite dimensional analog of the symplectification. It's going to be an infinite dimensional symplectic manifold. And it will turn out to be a dual symplectic pair. And if we do symplectic reduction of this dual symplectic pair at certain very nice levels, only level 0 will be feasible. Certain decorated nonlinear Grassmannians of isotropic submanifolds in the contact manifold will appear, and I will then explain how they describe some coadjuvant orbits. So this is the rough plan. Maybe let me say a few words about contact manifolds. Contact manifolds appear in many areas of mathematics and physics. They can certainly be traced back to this work of Sophus Lee from the 19th century, late 19th century, about contact transformations. They appear in classical mechanics, as advertised by Arnold. They appear in analysis, in particular in sub-Riemannian geometry. Think of the Heisenberg calculus, for instance. I suppose they are important in optimal control theory, but I don't know anything about that. They have applications in low-dimensional topology. There are some striking results. For instance, the Lutz-Martinet theorem tells us that every orientable three-manifold admits a contact structure. People have discovered exotic contact structures on the sphere, for instance. There is this topological classification of an Hirschberg of over-twisted contact structures on three manifolds, which apparently has been generalized recently to all contact manifolds. And that can actually be used to prove theorems in topology. There's apparently, I don't know about that, but there's apparently very substantial applications to knot theory. There is, for instance, Hirschberg's proof of Zerf's lemma, gamma 4 equals is trivial. There's a proof using contact topology, using his classification of tight contact structures on the sphere sphere. So this is a very active field, and it branches and has connections with many parts of mathematics. Contact manifolds can be understood as the odd-dimensional cousins of symplectic manifolds in many respects, and we will see many of these respects during this lecture. Okay, so let me start by recalling what a contact manifold is. A contact manifold is a smooth manifold that is equipped with the contact with the hyperplane field. A hyperplane field is just a smooth subbundle of co-rank 1 in the tangent bundle. So this is a contact manifold. Smooth manifold P and then hyperplane field psi co-rank 1 subbundle in the tangent bundle. So the contact manifold will be called P all along today, and psi will always be the contact plane field. This is supposed to be maximally non-integrable. That can be formulated by saying, by looking at the V bracket of vector fields, which induces a tensorial map that takes you from the second Wesch product of this hyperplane field into a line bundle that's naturally associated with your contact manifold by just quotienting out the hyperplane field. If you look at the V bracket, it's immediate that this is a tensorial object here. And for a contact manifold, one requires that this skew-symmetric two-form with values in the line bundle, so this is more or less a skew-symmetric two-form that is supposed to be non-degenerate. That's what one means by saying it is maximally non-integrable. Integrable would mean that the V brackets of sections of psi are again containing psi. That just would mean that this bracket has 0. That is the other extreme, and in this case we would have Frobenius and leaves. Yeah, so this is a skew-symmetric two-form on each of these hyperplanes psi. In particular, the rank of psi has to be even. It's linear algebra, just like expected. Linear algebra, and so the dimension of P is odd. So here you have an odd dimensional cosmos. Often, the hyperplane field can be written as the kernel of a one form. This is so alpha is a one form. This is a minor restriction. Locally, it's certainly always possible. Globally, there's a minor obstruction. You can always pass to a twofold covering, and then there it will be possible.
Can you elaborate on this?
Why is can be written like that?
Why twofold covering works globally? And
well, you can trivialize this real line bundle by just passing to the covering that consists of the two orientations of this line bundle. And on this covering, there always is a. So on this covering, the cubic of this line bundle is trivializable, and then you can write on it. So this is a minor, not important restriction to use the alpha here. More important, I would say, is that in alpha we have an ambiguity. Different alphas can describe the same contact structure if they just differ by a multiplicative constant. And the contact structure is really just a hyperplane field, not the form. The form has the advantage that you can easily write down what it means to be maximally non-degenerate using the exterior calculus. So it just means that the expression alpha wedge T alpha to the n is non-zero pointwise everywhere. So it's a volume form. So we have a taboo theorem for contact structures. The taboo theory for contact structures, actually contact forms, tells you that locally the alpha is always of the form dz plus x1 dy1. There's a local normal form for contact forms. This is called Taboo's theorem. It tells you that there are no local invariants. Locally, contact manifolds all look alike. So this is another respect or instance where they like seem very similar to symplectic manifolds. There are not many geometries with this, normal forms, in particular geometries that are determined by distributions. The other kind I know of are angle structures. Certain four-dimensional geometries, a two-plane field is the geometry, and there we have local normal forms too. These are the stable distributions, contact distributions, angle distributions, and foliations. And that's it, I think, as a classification. There's not many geometries determined by distributions that have local normal forms. Yeah, let me give you a few examples. First example, the projectivized cotangent bundle. Take any manifold Q, we look at the cotangent bundle, we projectivize it, so that means we remove the zero section and model out the action of the reals, so that are dilations. And on the cotangent bundle, we have a canonical one form. This canonical one form is homogeneous with respect to this action, and that just means that the kernel of this one form comes from a distribution on the base. So on the base of this projectivized cotangent bundle, there's a canonical contact structure, though there's no canonical contact form. So this is one.
So the canonical one form is PDQ, and then it goes.
It's homogeneous with respect to this action. So the kernel.
Can you get this alpha from this PDQ? Can you get alpha from PDQ?
You cannot write down a canonical alpha, a form on the project first, because it's homogeneous. The alpha will not descend, but its kernel will. You can't write down an alpha in the base that takes values in the line bundle. I don't
But
know.
this local formula doesn't get from PDQ.
Not in this form, not with an honest one form on the projectivized cotangent bundle. You would have to use it one form with values in some line bundle, which I'm not prepared to do.
No, but this is locally line bundle is trivial, so it's a local form, maybe just. But okay, could be.
Yeah, just locally you still have the topology of projective space. Okay, so this is certainly one classical important example. Another example we will actually use jet spaces. So let's look at the one jet functions on the manifold Q. So by this I just mean Q plus R. So values and derivatives of so one jet of Q, and here we have an alpha, a contact form. We can take ET, this is the projection of the last factor, minus the canonical one form we have on T star Q. It's straightforward to verify that this is indeed a contact form. And it has the property that if we take a section of this one-shot bundle section, this bundle over Q, then this section has isotropic image. So contact manifolds and isotropic submanifold is a submanifold that's tangent to the contact distribution. So that means the contact form vanishes when you pull it back to the submanifold. So isotropic submanifolds, for linear algebra reasons, the dimension cannot exceed n. Almost half of the dimension of xi. Because now that gives isotropic subspaces in this spaces. So they play the same role as the Lagrangian or isotropic submanifolds in symplectic topology. So a subspace, the image of such a section is isotropic if and only if it is the jet of a function. If and only if there exists a function of Q such that this section was the one jet of the function. So that encodes this integrability condition. When is a section of the one jet bundle the one jet of a function? That is precisely characterized by the contact structure on the one jet bundle, which and by the fact by saying that its image is isotropic submanifold. So this is sometimes called polynomial. Second example, the third example I would like to mention is the Hessenberg group. Hessenberg group. Dimensional Lie group. Yeah. It has a left invariant contact structure, but just translating this codimension one space for us. Yeah, maybe let me mention two more theorems that are available for contact manifolds and that are very analogous to what we have in symplectic geometry and topology. One is ray stability. If you have a smooth one-parameter family of contact structures, then there's an isotopy that implements this family. So if you have a smooth family of contact structures that depends smoothly on a real parameter T, then there is an isotopy, like the curve of diffeomorphisms Ft, right, Pt, such that they all diffeomorphic to psi norm. This can be proved with the Moser trick. Very similar to the proof in the symplectic geometry. And the last thing I'd like to mention that we have normal forms along near isotropic submanifolds. Like in particular, near the Legendrian submanifolds, these isotropic submanifolds of maximum dimension n. There's a normal form, you know exactly how the contact structure looks near such Legendrian submanifold. Okay, so these are already some very well-known features of contact manifolds, and they resemble the symplectic category very much. The next thing I would like to talk about is the group of contact diffeomorphisms. So the group of contact diffeomorphisms is just a group of all diffeomorphisms which preserve the contact structure, and the contact structure is the hyperplane field. So these are all diffeomorphisms G. So this will turn out to be very much like the Hamiltonian group. You can of course rephrase that in terms of the contact form. That would be all diffeomorphisms of P, such that when you pull back the contact form, you get a multiple of the contact form. There's a conformal factor A, and the contact form is preserved up to this conformal factor. This is precisely the condition that means that the kernel remains the same. So this is the group of contact diffeomorphism. And of course, you can wonder what is the infinitesimal analog or the infinitesimal version. So you look at vector fields. So these are vector fields whose flow preserves the psi, and that can be worked out in this description, for instance, easily precisely the vector fields on P, such that the Lie derivative of alpha is a multiple of alpha up to a conformal factor. The Lie derivative preserves the vector field. And in fact, you can easily check that if you know alpha of your vector field, this is just one function. You contract the vector field with alpha. This is a function. If you know this function, you can completely recover the vector field using this equation here. I'm not going to do that as playing around with the real vector field. But that tells you that the vector fields can also be understood as sections of this line boundary I introduced before. So if you have a vector field, and any vector field will give you a section of this line boundary, you might just like see what it induces on this line boundary. But if it was a contact vector field, then from this section here, you can reconstruct the whole contact vector field, something like a contact gradient.
How does the line bundle come into the game?
Well, from the tangent bundle of P, you can project into L. This is like extracting one component of the X, like the one that's transversal to the contact plane field. If you know this component, the remaining components are totally fixed by this condition here. It's like a contact gradient. I'm not going to do that. You have to play around with the real vector field and the relations we cherish for the Cartan calculus.
What was the real vector field?
This is a canonical vector field associated to the contact form that is really not in the spirit of my talk, and so I'm sweeping that as well. So, and if we're using an alpha, we can also trivialize this line bundle, and these are just functions. Sections of a line bundle up to this trivialization, which is not canonical, but we can still do that, and then it's just functions. The contact vector fields are essentially functions on the manifold. Like in symplectic geometry, the Hamiltonian vector fields are essentially functions. So there's no ambiguity there. No. So even if the function is constant, you still get a non-trivial contact vector field.
The bundle is always trivial, this line bundle.
No, but if it is, then we can do that.
Okay.
And that will require alpha, and it's not canonical. Some people find it easier to think of functions as sections and line bundles. So I tried to decide on one point of view, I couldn't, so I'm giving you both. Yeah, that's some more room. This group of contact diffeomorphisms is a very nice group. It's well known that this is an infinite dimensional Lie group, and it is modeled on the functions on P. More precisely, it's modeled on the Lie algebra, on the sections of this line bundle. And a chart, the standard charts we have for this group are called Weinstein charts. They're similar to the symplectic geometry. These are charts that show you that the group of contact diffeomorphisms is modeled on the function space functions on M. For the contact setting, this has been adapted by the Chagi, if I'm not mistaken. And I'd like to recall that construction for you, because I think it's a very beautiful construction. That's going to use the normal form near Legendre submanifolds, near isotropic submanifolds. So there's two contact manifolds one studies here. One studies the one jets on P. This is the contact manifold I showed you before. Then we have the contact structure given by dt minus the canonical. So this is T star P cross R. We have the canonical one form on T star P and dt from the projection of the second factor. So this is certainly a contact manifold. I showed you that before, and I also told you what the isotropic submanifolds are. At least I showed you that sections of this bundle are isotropic if and only if they come from functions. And the second contact manifold one considers here is something like a product. This the third factor. It's non-zero. On this product, so this is again an odd-dimensional manifold. On this product, we have a contact form T times the pullback of alpha by the first projection minus the pullback of alpha by the second projection. So I'm assuming for simplicity that the contact structure of P can be described by a contact form, which is very convenient at this point. Otherwise, one ends up doing gymnastics with natural bundles, which is not easy to communicate. So there are two Legendre submanifolds here. Here we have the zero section. So differential to P, and here we have the diagonal. So diagonal here is 0, and here we just put once for the diagonal. These are easily checked to be isotropic submanifolds of maximal dimension. So these are the Legendre submanifolds. And this tubular neighborhood I mentioned to you, these normal forms we have along the Legendre manifolds, I'll tell you that there's a neighborhood of this zero section here that we call it U, and there's a neighborhood of this diagonal here, we call it V. And these two neighborhoods are diffeomorphic as contact manifolds. So there's a contact diffeomorphism, and I will call it theta. Contact diffeomorphism. In particular, this is what we're going to use. Isotropic submanifolds in U correspond to isotropic submanifolds in V, just because it's a contact diffeomorphism. This is the main point. And then this can be used to write down the chart for the group of contact diffeomorphisms. You start with a function on P, which is, I think we need C2 close to 0. Then we take the watershed. So we take the watershed of this function. So we just look at the function and its derivative, and we look at its image. And by definition of the contact structure here, this image is a submanifold which is isotropic. This is isotropic. Well, in U, if we are sufficiently close to 0 here, it's isotropic in U, and it's still C1 close to the zero section P. Then we can move that using this contact diffeomorphism, and we look at theta composed with the watershed. This is a map into this diagonal. We can look at its image. And we know that this is isotropic in V. The fact I mentioned before, it's a contact diffeomorphism maps isotropic submanifolds to isotropic submanifolds. And it's still going to be C1 close to the diagonal here, to the P. Well, there's something like a bijection. If it's sufficiently close to the diagonal, then composing with the projection onto the first P is a diffeomorphism, and composing onto the projection with the second P is a diffeomorphism. And you can combine that. You look at You look at the projection, compose it with the projection onto the first P. So this is now a map from P to P. It's a diffeomorphism because we're close enough to the diagonal here. We take the inverse and we compose that with the same expression we get using the second projection. Now this is a diffeomorphism. And if you look at the contact form here, being the image is an isotropic submanifold. If you look what that means, that just means that this is now a contact diffeomorphism. And this conformal factor is precisely provided by the third component. So it's clear that this is a contact diffeomorphism with conformal factor provided by projecting out the third component. This is what the point about this, looking at this contact structure is. We can like characterize as contact diffeomorphisms by as isotropic submanifolds. So this is a contact diffeomorphism, and it's C1 close to the identity, because this corresponds to the diagonal. And then you think a little more, and you can go backwards, and you end up with a chart, a bijection that identifies a C2 neighborhood of 0 on the functions, with a C1 neighborhood of the identity in the contact group. And in this sense, the group is modeled on the functions. And this can be used as a chart, and then you check that this provides, or this can be used to equip the group with the structure of a V group, and the details about that can all be found in Peter Michael and Andreas Kelly's book. It's very, very easy from this point, from this point on, once you have their calculus at hand. So the point is, this is a V group. It's locally modeled. Sorry. On the V algebra is let me write compact supports. Compactly supported vector field. So this is really compactly supported sections of this line bundle we had, and if you prefer, you can identify this with compactly supported functions. Okay. Yeah, so in this way, the group of contact diffeomorphisms can be turned into a Lie group. So we see it's a huge group. For each function, we have a group element at least, and it's going to act very transitively on our manifold, just like the Hamiltonian group does. Okay. Good. Next, I'd like to turn to this symplectification. The natural construction that takes a contact manifold and produces a symplectic manifold. And this is the construction we're going to generalize to produce this nonlinear Grassmannians associated with contact manifolds. So simplification. So recall the line bundle we had was TP mod psi, quotient of the tangent bundle. So if we look at the dual line bundle, then this is going to be contained in the cotangent bundle. The cotangent bundle, there's a canonical one form. We can pull the canonical one form back to the total space of L star, and we're going to get a canonical one form on this dual bundle. Theta, so one form we get on the total space of this line bundle. And one way to understand what the theta is just a pullback of the canonical one form. P star P. If you prefer using contact form, then you can use contact form to trivialize this line bundle L star. And in this trivialization, the theta will just be T times alpha. Alpha, the contact form of P, that's being used to trivialize here. Pulled back, of course, and then T is a projection onto the second factor. This form is invariant under the compact group. Highly canonical. Every diffeomorphism of P acts on the cotangent bundle and preserves the canonical one form. The contact diffeomorphisms are precisely the diffeomorphisms that preserve the subbundle, and of course they are going to preserve the restriction of the one form to the subbundle. It's entirely obvious that this is invariant under the group. We can look at the differential of this theta. After all, the differential of the one form on the cotangent bundle is a symplectic form. So let's see what we get in this case here. What if we take the differential of this one form theta here? So I'm going to use this description here now. This is dt alpha plus alpha h theta t. And if we exterior power, then we get n dt alpha t alpha to the minus 1. No, I need n plus power. That's probably, yeah. That's probably in there. Something like that. The highest serial power of the omega has this form. And you see that because we start with the contact form, this here is non-zero. dt goes in totally different direction. So this is again non-vanishing as long as this factor doesn't vanish. So as soon as we remove 0 here, it's going to be symplectic. So omega symplectic on, well, L star minus the 0 section, or if you prefer P, is R minus 0. So this is then we have a symplectic form. The symplectic form is invariant under the contact group, but in fact the symplectic form is exact, and this antiderivative is this theta is invariant. So we have this group X and preserves the theta. So this is going to be a Hamiltonian action, and it's going to come with a equivariant moment map. It's a very general principle. You have an exact symplectic manifold, and the theta is conserved to get equivariant moment maps. We've heard about that before this week, so I'm not going to recall much about this general formalism here. Let me just write down the moment map. Victoria. With equivariant. So here is the manifold. We have an equivariant moment map J, and this is going to take us to, yeah, I'm going to write down formulas in a second. Going to be, well, it's going to be the dual of the Lie algebra. And the dual of the Lie algebra is something like distributions on P, but it's real distributional densities on P. So this is my notation for the density bundle on P. So the geometric objects you can integrate canonically, and these distributional versions of that. So this is the dual of the functions on P. And this is why this the dual of the Lie algebra. So this is where the moment map is going to take values. So maybe I write down the formulas as explicit as possible for the action here, and for the moment map. So here's the group that acts here. The group I will call it G. This is the difference of P. it acts from the left on a pair pointing P and a parameter T, and the action is just you apply the differential to the point in P. And well, you have to multiply the T by the conformal factor that's provided by the contact differential. So the contact differential has a conformal factor. You write it like that. That was the HG before. You have to evaluate that at X and multiply the T. So this is the action here doesn't look so natural, but this is just because we use the alpha to trivialize something that is, and the trivialization was not natural, and at this point we're paying the price. The action looks a little weird. We have this conformal factor here. Similarly, the action, the coadjuvant action we have on G, because in this identification the alpha is contained, we will too have a conformal factor popping up in the action. If we act on a distribution here, it's not just the push forward of the distribution. It has to be corrected by a conformal factor, which in this case is alpha over. Again, this unnatural looking action here stems from the fact that we have actually identified using a complex form, which is not canonical.
So the push forward is the inverse of the pullback by the inverse, or?
Yeah, distributions you push them forward because the test functions are being pulled back. And the moment map is very simple in this case. To a point X in P and the parameter T, we just associate the delta function at X, delta distribution at X, Dirac delta times T. This is what you get. This is you don't have to guess that, you just work it out because you know the moment map is just given by contracting the theta with the infinitesimal action. You work out what the infinitesimal action is, contract, and this is what pops up. Okay, so this is the toy example. Some parts are already infinite dimensional here. The group is acting is infinite dimensional, but the space on which it's acting is still finite dimensional. This is the toy example, and we will soon generalize this construction here, and then this space will become infinite dimensional too. But let me say a few words what you can say about this action here. The group acts transitively on this manifold in a very nice way. The action admits local sections, local smooth sections. So in particular, it acts locally transitively. This kind of argument, to prove that, you just need the finite dimensional implicit function theorem, finite dimensional inverse function theorem. This argument can be found in a paper by Peter Michael and Cornelia Wiesmann. This kind of arguments one, this kind of transitivity proofs. Also, if you look at the isotropy group of the action here, so the group is infinite dimensional, nice Lie group. But if you look at the isotropy group, you can actually show that it's a closed splitting Lie subgroup. It's a very nice subgroup. This is also not very hard to show in this case because the space on which it acts is finite dimensional. And this also means that the orbits of the action here, which are open subsets because the action is transitive, locally transitive, they can be regarded as homogeneous spaces of this infinite dimensional group. So the isotropy is a subgroup, and the orbit map actually can be locally trivialized because there's local splittings of this action. So the orbits here can be described as homogeneous spaces of this infinite dimensional group too, in a very rigorous sense in the category of infinite dimensional manifolds.
You say all of P, right? Because this is just one orbit. You said it's transitive.
I should say locally transitive. So the arguments are always you have local smooth sections that gives you local transitivity. If you want global transitivity, you have to work and use totally different tools. Though in this case, if P is connected and say A is non-orientable, then it's going to be connected and then it would have to be everything. So that you can argue like that sometimes, but not always. Yeah, and then you can wonder what this constant Kirillov-Fourier symplectic form we have on the coadjoint orbits here. So of course then, I'm sorry, I should say that this is going to be injective, which is clear from the formula here. It's going to be injective and it's parameterizing certain coadjoint orbits. Yeah, because the action here is transitive and it's locally transitive. So each of these orbits we have here is just parameterizing a coadjoint orbit here. So we're parameterizing very special, very simple coadjoint orbits, which are given by delta distributions. Nevertheless, you can ask what about the symplectic form? What if you pull back the canonical symplectic form we have here? Well, and lo and behold, this is just the symplectic form on this manifold. So if you take the constant Kirillov-Fourier symplectic form, if you pull it back, you get the symplectic form we had on this manifold. This is just a formal consequence of the fact that this is an equivariant moment map. So this can be used to parameterize certain coadjoint orbits, including the symplectic structure. That's one thing you can do, and this is what we're going to generalize soon. And the other thing you can try to do using this moment map is to study the algebroid equation, so the geodesic equation on the group, and try to study singular solutions of this equation using this moment map. And I would like to show you what that would look like in this example where it's just delta distributions supported on points. And this is another point we will generalize later on. So the geodesic equation on the group is associated with an inner product on the Lie algebra. So we will describe this inner product with so-called inertia operator. Let me just first be kind of sketchy. Let's take an inertia operator, just a linear operator. Let me not be specific at this point yet. It's supposed to be symmetric and positive, and we use that to write down an inner product on an inner product on the Lie algebra. And that gives rise to writing the Riemannian metric under quotation marks, because it's just formal at this point yet. And this inner product should give rise to a geodesic equation under the algebra. This is the Euler-Arnold equation we referred to before. Just the time derivative is minus the transpose of the adjoint action of U in itself. Then you can look at the momentum.
How does U enter here? Because transpose.
So the geodesic equation, you do look at the right trivialized version. So you get an equation for the right logarithmic derivative. This is a curve in the Lie algebra.
Is it transposed?
Transposed, yeah.
And that's used to.
You look at the adjoint action of U, it's transposed, and you apply it to U.
But the transpose is use Q, right? Uses this.
Transposed is with respect to this inner product.
That was the question.
Yeah, you're right. Yeah, transposed with respect to inner product, and of course, yeah, can be written in terms of the co-adjoint action using Q and Q inverse. So this is just formal at this point. I will soon be way more specific about what operator Q we are going to study, and then this can be made very precise. So if you look at the momentum, I apply Q. So this is now in G star. Then here's the Poisson equation. So the time derivative is minus add, well, Q inverse of M applied to M. This is the coadjoint action. But here on the dual of the D algebra, it's actually a Hamiltonian equation. This is just a Hamiltonian vector field of M. And the Hamiltonian H is function on G star, and this function is just in Q. This is the general formal aspects, and we've heard on several instances in this during this conference already. So I would like to use it now in this context. So we're here on G star, we have this Hamiltonian and the subjective form, a Hamiltonian equation. We know what the subjective form goes back here. Let's try to go back to Hamiltonian 2 and see what question we get here. Maybe we can solve the equation here, which is after all finite dimensional, and then we will get singular solutions in G star. This is the plan. So let's try to go back to Hamiltonian. And to be able to do that, we have to be specific about what inertial operators we are using. So the Q should be an absolute differential operator of some order S. Well, it's essentially taking functions to functions, functions on P to functions on P. But what it really should do is it should take sections of this line bundle A to sections of the dual bundle tensorized with the densities. So it should take some sections of some line bundle to sections of some other line bundle. This is the natural setup. Essentially, it's a pseudo differential operator on functions. And that just provides exactly an operator of this form. Only now it's we have way better control about what the operator does on this overlap scale, because we specified the order of the operator and the assumptions we need to in order to put it through. Yes, this should be symmetric, this should be positive, it should be invertible, and the inverse should be to the differential operator from all analysis.
It's globally invertible.
Globally invertible, and at this point I would like to restrict to compact P, to closed P. I do not want to deal with compact supports during this part of the talk. So far, P was arbitrary. So operators of this form can easily be constructed. You take a power of Laplacian, you take Laplacian plus 1, and you take the power S of this Laplacian, and you get operator of this form by elliptic theory. The inverse is going to be of this type. Yeah, then in this case, we can write down the Hamiltonian. The Hamiltonian of M is then just 1/2. Well, we have to integrate M against the kernel of this inverse. I'm just spelling out what this expression looks like now that this is a pseudo differential operator. We can use its kernel to write this. And if we assume, no, we don't have to assume like that. This is actually it's not defined on all distributions, because it's not defined on all of G star. But it is defined on distributions which are also left as S minus S over 2. what do we have here? Here, this operator, this Hamiltonian M is well defined. Just by continuity. So this is Sobolev minus S over 2. This is Sobolev minus S over 2, and this has this is an operator of order S. This is going to be L2. We can integrate that. So this is well defined on this subspace of distributions. The distributions have regularity minus S over 2 and Sobolev scale, and then the Hamilton function is defined. And if we assume that the S is larger than the dimension of P, then our moment map that's coming from P. Well, it takes values in the distributions, but if you look at the formula, it's delta distributions, so the regularity is not too bad. It certainly end up in exactly this Sobolev space here. We certainly end up in Sobolev distributions of Sobolev plus minus S over 2. This is just by that's a tip. Okay, so we can compose them. We can actually compose the Hamiltonian we have on G star with our moment map J, and we get the map that's defined on our finite dimensional symplectic manifold P. It's very small. And if you look what that function what you get by using the expression here. For M, you plug in the delta distribution, then you see that the Hamiltonian at the point x t is just t squared over 2. The kernel of the inverse of this inertia operator is evaluated at the diagonal. And the operator q to the power minus 1, this is assumed to be of Sobolev. This is an operator of order minus s. So this is minus s is larger than minus, is smaller than minus the dimension of p. So the kernel of this operator is going to be continuous, just by the order it has. It's going to be continuous, so we can restrict it to diagonal. We get honest values here. This is well defined because the kernel is continuous there, and it's going to be smooth in X. It's going to be smooth in X because it's actually a pseudo-differential operator we used. So far, before this observation here, smoothness in X, we've just used that it behaves well with respect to the Sobolev scale. But at this point, if you want the restriction to the diagonal to be smooth, you need nice operators. And pseudo-differential operators have this property. So in this case, we can pull back the Hamiltonian function, and this is a nice smooth function of this finite-dimensional symplectic manifold. Then we can solve the Hamiltonian equation, and then we can move back. We get solutions of the Hamiltonian equation in here. These are the equations for the momenta. They are singular, they're distributional, they are supported at points, delta distributions that move around. And then if we move back to the velocity, that's the curve in G, they are going to be continuous. This is a Sobolev embedding. They will be like singular, non-differentiable at this point where the momentum is supported, but outside, away from this point, they're going to be smooth. It's just pseudo locality of the operator because the momentum is 0 away from the point x where it's supported. And if you apply pseudo differential operator, it remains smooth there. But overall, it's going to be continuous. So this is what people call peak-on solutions. So this can be used to make an observation rigorous that has been laid out by Eben and Preston in a paper. They suggested exactly that. They suggested to study singular solutions of the geodesic equation of G star. Study then where the momentum is located or supported on submanifolds. And this is one way to make it rigorous where the submanifolds are points. And running out of time, but tomorrow I will talk about how to generalize the symplectification, and this will then give you similar approach to singular solutions that are supported on submanifolds, where the momentum is supported on submanifolds. Okay, I guess I have to stop here. And thank you for your attention.
Thank you, Stefan, for the talk. We will take now online questions first, if there are any. If there aren't, I'm going to ask the audience in Vienna if they have any question. I'm coming.
So how explicit can you get these Poisson solutions for other equations using this formalism? Like, does it just produce, theoretically there exists something, or you can actually write down formulas for them? Like, for example,
well, the Hamiltonian here looks very, very simple. I have not tried to actually solve this equation explicitly. In particular, I have not tried to use particular Q's. I know that you used the Laplacian plus one. Well, I have not done any explicit computations.
Any questions? Okay.
Can you give a simple example of the singular solutions, like one, to have an idea what you mean by singular solution?
It is so that the momentum will be of this form. It will be density distribution. The point where it's supported is going to move around. The weight is going to change. This is the momentum. Everywhere else it's zero.
So it's a solution in the distributions.
Yes. So this is the momentum. The velocity, you get the velocity by applying Q. So Q inverse. Q inverse has one minus S, so it's regularizing it. The velocity will be like smoother. And in fact, the velocity will be continuous just by Sobolev embedding, because this it's going to be continuous, but at this point where the momentum was supported, it's not going to be differentiable. But away from this point, it's going to be smooth, because that was obtained by applying the Q inverse, a pseudo differential operator, to something that was already smooth there. So you don't lose this property. The singular spot doesn't get bigger. So it's going to be smooth everywhere, except at the points where the momentum is supported. But that's still going to be continuous. And this is, as far as I understand, what people call peak-on solutions for the velocity.
Mm-hmm.
Do we have any other questions? If not, then we
I have a question. Sorry.
The question you can ask.
So in your discussion, I guess in particular about the Hamiltonian action for the contact diffeomorphisms, can you give a sense of like what sort of things you end up really having to check to make sure it works because of the infinite dimensional setting?
Well, not much. Everything we're doing over here is really formal, and over here is finite dimensional in this case. So there's really like very little you have to.
So this thing about because the form is exact, you know, the action's Hamiltonian, is that clear for the infinite dimensional setting? Or like infinite dimensional Lie group actions?
Yeah, you get the Hamilton functions by contracting.
Oh, yeah.
Infinitesimal action. So The infinitesimal action is an infinite dimensional group, but it's still acting on a finite dimensional manifold, so it's like vector fields.
Yeah, so it's because you're acting on finite dimensional space. I guess that's not so bad.
Contract the vector field with a
All right, thanks.
Are
All
there
right, thanks.
So from my point of view, more troublesome is the structure of the coordinate orbits here. This is like totally not clear to me what they look like, but parameterizations like that allow you to understand some very special coordinate orbits in a differential geometric way. You actually parameterize it with something very smooth and manifold like, and you could, yeah. But in general, the general coordinate orbits, I do not know how to treat them with these tools.
We will thank Stefan again.